Alright, we will have a we have already covered what is the basics of flight dynamics as well as many things about classical control system as well as state space representation so far. So, this particular lecture and next we will study a small overview about flight dynamics, so that we can connect the material what is going on here for aerospace guidance and control. So, this particular lecture will take you through this so called point mass equations as well as a major portion of what is called a Sixtov equation, and then we will follow that up in the next class with further concept which will make us ready for understanding the relationship between what we are studying in the control theory to aerospace applications actually. So, this is the first we will see point mass dynamics, and it all depends on your application, how you want to visualize this aerospace dynamics actually. Suppose you are interested in a long term trajectory, okay, then probably point mass equations are sufficient, because you don't need to know the attitude of the vehicle at any point of time. You just need to know the location of the vehicle as well as its velocity and velocity direction in a gross sense. So, really do not need to have all details about the vehicle attitude, vehicle roll rate and pitch rate, things like that for a long duration application. That is where this point mass equation becomes relevant, and it is mostly used for guidance applications actually. So, let us see what is what is called as point mass dynamics, and we are essentially visualizing the entire vehicle as a point moving in space. Okay, so we will and then relevant equations we will see what all variables are there and things like that. So, basic assumptions for point mass model. First of all, we are all kind of collapsing the entire vehicle at the CG of the airplane. So, that means all forces act on the CG of the airplane, then the entire vehicle is just a point, and acceleration due to gravity is constant. We are not bothered about variation of g, unless you talk about a very long very kind of interplanetary missions and things like that, when you really go far away from Earth actually. Okay. Otherwise, for most of the applications we can fairly assume that gravity is constant. Then atmosphere is rest relative to Earth, we are not considered about this wind effects and all that. Okay. And atmosphere properties are also functions of altitude only. Okay. We will consider this, especially we know that dynamic pressure is a quantity which is which depends on density of atmosphere, and that varies with height. Okay. So, atmosphere properties we will consider only as a function of height, nothing else actually. Okay. And the force acting on the airplane are thrust, aerodynamic forces and its weight. We will see that in a vectorial diagram next slide actually. Vehicle attitude is ignored, as I told, the which angle it is oriented and things like that is not of our concern here. However, the direction of velocity vector is of primary importance, because that will govern the trajectory of the vehicle in the long run actually. So, this is pictorially, this is where the vehicle is located, the entire vehicle is just a point here, okay, and let us say the vehicle is moving in that direction v, okay, that is the total velocity of the vehicle, and this x is actually like parallel to the local horizontal. Okay. So, whatever angle that this velocity vector makes with respect to the local horizontal plane, that is called flight path angle or gamma. Okay. And most likely the thrust vector is associated as aligned with respect to the vehicle x axis, okay, vehicle nose and things like that. However, there may be kind of alignments small angle with respect to the vehicle x axis, but we will not consider that here. What we will see is the thrust is aligned with respect to the vehicle x axis. In that sense, this angle what you see is angle of attack alpha. Okay. So, y is the altitude axis, and the x is the downrange thing actually. That means, wherever this flight goes, we are considering only on that plane. Okay. This is not a 3-dimensional picture, it is just a 2-dimensional in the pitch plane sort of thing actually. So, this vehicle, this velocity vector v is can rotate, okay, depending on this alpha actually, because thrust is the thing, it is not aligned with the velocity vector, and hence it will have a component perpendicular to the velocity vector, which will result in orientation, which will take this velocity vector away. That means, gamma will alter because of alpha basically. Okay. So, with respect to that, let us resolve the component in various planes. Now, we have this, we know that drag acts directly opposing to the velocity. So, drag is straight away opposing to the velocity. And thrust, lift is perpendicular to the drag or perpendicular to the velocity vector. So, that is how it is, alright. And then weight, we know it is perpendicular to the local horizontal. So, weight will always act perpendicular gravitational weight, and thrust is anyway there. So, we are interested in this velocity level equation and acceleration level equations actually. Okay. Now, let us see, velocity level equations are nothing but simply components of the velocity vector in x and y direction actually, that is all. So, what you have here, this velocity vector, if this angle is gamma, then this is actually x dot and that is h dot, okay. And then this is x dot is obviously v cos gamma and h dot is v sin gamma. This is simply the component of velocity vector in horizontal and vertical plane. Nothing there, simple geometry tells us that one actually. However, you want to have a moment level equations, the force level equation next, that will give that will be resolved again into this perpendicular directions and things like that. Before you do that, let us also remember that this velocity level equations do not see forces and do not see vehicle parameters. They are simply related by geometrical relationship. These are called kinematic equations. So, you will have two kinematic equations coming here, x dot is v cos gamma and h dot is v sin gamma. The next is dynamic equations, where your thrust and weight, vehicle parameters, everything will come into picture. Let us see how to resolve that. So, this particular thing will resolve one along the velocity vector direction, and one perpendicular to that, all the forces that is acting on there. So, what are the total forces acting on this particular direction? Okay, one component comes from thrust, so that is given as T cos alpha. One is opposing to that, that is minus d. So, you have T cos alpha minus d, and W has also a perpendicular, W has a component because there is a gamma angle that is acting on that actually. So, if you see W, the W has a component which is W sin gamma, which is negative to V actually. Okay. So, if you have T cos alpha minus d minus W sin gamma, that is the net force acting along y direction, velocity direction, and hence by Newton's second law, this is mv dot. So, mv dot is nothing but T cosine alpha minus d minus W sin gamma, okay, whatever component. So, that is what it comes there. And similarly, once you try to kind of resolve this along the vertical direction, this perpendicular to the velocity vector, then see that this is there is a thrust component again, that is T sin alpha this time, plus lift component, okay, minus W cosine gamma, okay, this component is also there. Okay, so, that is what you see here, and that is all equal to the net resulting force acting on that direction. Remember that is like centrifugal force and things like that, you can assume that way. So, if you this particular thing is nothing but mv gamma dot actually, okay, m times v into gamma dot. Remember, this is actually a force quantity, this is acceleration quantity v times gamma dot, and mv gamma dot is a force quantity, and that is like centripetal force sort of thing actually. So, if you imagine a circle somewhere here passing there, but velocity vector is tangent to that. Okay, if you imagine a circle, okay, passing through this point where velocity vector is tangent to that, then the net resulting centripetal force will be somewhere mv gamma dot actually. Okay. So, that is how you see that. That is how this gamma dot is will start changing actually. Okay. So, if you divide the entire quantity by m, you will get v dot. If you divide the entire quantity by mv, you will get gamma dot. So, putting everything together, so what you get? X dot is v cosine gamma, h dot is v sin gamma, v dot is that, and gamma dot is that actually. Okay. And typically in this kind of problems, we interpret alpha as the control variable, because that is where we have the liberty of changing alpha basically. Okay. So, that is suppose if you go back to that, if you see especially a rocket, let us say, then we have a thrust vectoring facility, that means thrust can be tilted out, that means this thrust deflection can happen, it need not be aligned with respect to the vehicle nose actually. Okay. So, that is that can act as a control variable really. Aerodynamic variable also it is same. You can manipulate alpha by reflecting the control surfaces through aerodynamic forces actually. Alright, so putting together, this is the set of equations in state space is form that we talk as long as we talk about flat earth model point mass equations. So, the earth is flat, okay, and it's not rotating, okay, and under several assumptions that several other assumptions that we talked here actually, okay. So, under those assumptions we will consider these are set of equations that to deal with, where x, h, v, gamma are state variables, let us say, and then your alpha is control variable, okay, and d and l, remember they are also functions of alpha, okay, drag and lift, they are certainly functions of alpha actually, okay, and especially this mass quantity, okay, and thrust, we interpret them as parameters actually. Okay. Thrust can be constant in aircraft applications, thrust can be time varying in rocket applications actually. Okay. Thrust and mass both can be time varying if it is a launch vehicle or missile application basically, by the way. So, thrust and mass are considered as time varying parameters, x, h, v, gamma are state variables, okay, and g is also a parameter by the way, and then alpha is a control variable here. So, that is how the state equations are there in this point mass model. Also note that this rest of the equation what you see here, h, v, gamma are decoupled from x dot, they are not really functions of x actually. Okay, h is, I mean this v dot and gamma dot are functions of h because through dynamic pressure, this lift and drag will depend on h actually, okay. Whereas this x is kind of decoupled. We still need to integrate and get a value for x if we really want to plot the trajectory. The trajectory is dictated by x and h, the coordinate of this particular CG location is dictated by x and h. So, we still need to use that equation for integrating. However, this for all practical purpose we can also solve a problem in h, v, gamma coordinate only basically. Okay. Now, next we go to this, let us try slightly complicate the matter here, and then you tell, okay, how about a spherical non-rotating earth? Earth is still non-rotating, but we now will consider long duration flights, let us say for example, ballistic missiles, they will really travel a very long distance before falling the somewhere actually. So, earth curvature you can you cannot neglect really. So, this effects has to be taken into account. In that sense, what happens? Now, let us say for a moment the vehicle is somewhere here, it is still a point, okay. Velocity is there somewhere, okay. Remember, this is no more tangential to the surface of earth. Surface of earth is somewhere here. This dotted line what you see B is surface of earth, okay. And then this is a point, okay, where the vehicle is currently flying, okay, with a velocity direction that which is certainly not parallel to the tangent which will result from there actually. Okay, so it is certainly has some flight path angle and all that actually. So, what you are interpreting? We are interpreting, let us say, to try to analyze the equations little bit better way. We will try to visualize this in a hypothetical circle parallel to earth actually. So, B is like surface of earth, A is the instantaneous hypothetical circle parallel to the surface of earth, okay. And D is also like let us say D is another one, okay, this dotted line which will require slightly later actually, okay. Anyway, so we are coming back to this, this has a thrust direction again which is again at an angle of alpha. This is now local horizontal, remember this circle is parallel to this dotted circle. So, obviously, this tangent is actually a local horizontal tangent actually, okay. So, then you have this angle which is gamma, okay, and that angle is alpha, and hence if you see that this is actually thrust direction which is this is drag which is opposing to velocity, and then lift has to be perpendicular to the velocity, okay. And we also know that negative lift direction is the centripetal force sort of thing, and hence we can visualize another imaginary circle around that, okay, for which, okay, the center of the circle, if you join this point, this will be like along the lift vector actually, okay. Now, we have several directions here, so we have to resolve it properly, and also remember this is a reference line, okay, this particular line is a reference line. Let us say this is launch point or something about which we want to calculate, we want to know how much range angle you have covered, theta is called as range angle actually, okay. The actual range is on the surface of earth. If you multiply theta with radius of earth RE, you will get the actual down range actually on the curvature, okay, on the curvature of the earth actually. Anyway, so now coming back to that, first is let us see again this kinematic equation sort of thing. We will also see this force balance equation first. So, if you see this this particular direction, okay, V cos gamma is along this and V sin gamma will be along that. Okay. So, if you see this mv cos gamma whole square by r is the instantaneous radius from center of earth, this is center of earth, then that is the force that is acting along that actually, okay, and that has to be balanced by mv square by r cos gamma actually, okay. So, mv square by r is here, okay, and into cos gamma component is here actually, okay, this particular component. So, you are resolving this force quantity, I mean this this velocity level equations and all that. Okay, one is I mean this one is acting along that, the balancing is acting along that actually. So, through that if you equate these two, you will get a relationship between this particular r, this is the radius of this hypothetical circle, okay, and this is the r that is instantaneous radius from center of earth actually, that is the relationship they will have. This big R and small r, they will satisfy this relationship actually because of this force balance. Now, we will go back and resolve this vector along local, horizontal and vertical, that is where it will result in kinematic equations. So, r dot is again like h dot, okay. So, that is along that perpendicular sense, there is nothing but V times sin gamma. Oh sorry, r dot is nothing but V times sin gamma actually, okay. R dot is like h dot. So, velocity is there which is not orthogonal to this line and hence it will have a component actually. R dot is V sin gamma and then r theta dot is nothing but the angle that you cover actually. Theta dot is, remember this theta dot is angle of rate of change of this angle, okay. So, r times theta dot what you see is actually what is covered in terms of this particular direction. Suppose you take this way the velocity, okay. Velocity tangential to this, okay, this particular thing will have r theta dot and that is nothing but V cosine gamma actually, okay. So, r dot is V sin gamma again, that is similar, and instead of x dot, I mean what we saw in the last time it is x dot, that is like if you are flat earth it is x dot. Now, spherical earth is r times theta dot which is similar to x dot actually. So, r theta dot is V cos gamma actually, okay. Again similar quantity here. Then the next one is slightly complicated and you see that, okay, what happens to the other one actually. So, you are interested in mv dot, okay, and mv dot is almost similar to what we had the last time again. So, this is T cosine alpha, one component coming from thrust minus drag, okay, and mg is acting along that direction, w is nothing but mg into sin gamma component will also, I mean, act along this direction actually. So, mv dot is T cosine alpha minus d minus mg sin gamma. Now, we have to resolve, okay, one direction is that, the perpendicular direction to that is that one, okay, that is where this gamma dot equation will pop up. Again this mp gamma dot is the net resulting force along this direction, and here you can see that one component comes from T sin alpha from the thrust, there is a lift vector acting along that, there is a gravity component which is there subtracting that mg cosine gamma, and there is a mv square by r which is actually centrifugal force. And here we have derived a relationship between big R and small r. So, that is where you can use that, substitute that and then simplify this equation in terms of r. Remember our equation is r dot, okay, and big R is not a decoupled I mean relationship from r actually. So, big R and small r are related. So, it cannot be an independent variable, okay. So, we will substitute this big R in terms of small r and then simplify the equation in the state space form again. So, what you are getting, r dot is V sin gamma and r theta dot is V cos gamma, hence theta dot is V cos gamma by r, and then V dot is what you saw here, okay, that is the V dot equation divided by mass, and gamma dot is divided, all these divided by mv actually, okay. Alright. So, if you simplify that you will get everything there actually. So, this is what you will get, okay. Remember this r is also a function of this r and gamma, that is what we saw here actually, okay. You have to substitute that big R actually. So, these are the set of equations that we have to deal with as when we talk about spherical, but not rotating Earth. Okay, that means Earth is not rotating, and Earth rotation does play a role depending on if depending on the system equation. Actually, suppose you want to start with latitude, longitude, go to different lat long and things like that, then as long as they are not in the same latitude plane, then things will be different actually. So, for that I will not derive the equations and all, but these relationships are available. So, then things will be getting slightly more and more complicated as you talk about more and more effects coming into picture, and this will be more and more close to reality, of course. So, for spherical and rotating Earth, if you talk about, then you have r dot. Now, you cannot talk about only theta, because that was along the what is called as okay. I forgot to mention, this dynamics what you are deriving is all valid in the great circle actually. Great circle means suppose you are going from one point to other point, okay, and suppose let us say if your launch point is somewhere here, you want to go somewhere here, okay, on the surface of Earth, wherever you want to go. So, that is the launch point, target point and center of Earth. They are three different points actually. Okay. So, these 3 points when you connect, obviously that will go through that will intersect the Earth center, and it will result in the greatest circle actually. Anything parallel to that will be small radius circle. Okay. So, because of that it is called a great circle, and whatever equations we saw here is all valid in the great circle plane actually. Okay. So, we are not consider the 3D equations, this cross cross range motions and things like that. It is all down range motion still. Okay. But here we will not worry about that. We are talking about the entire 3D movement sort of thing. We consider rotating Earth also into picture, and hence all the equations, all the things we have to take into account actually. Okay. So, phi and theta are lat-long positions here, and r dot is still v sin gamma, but you will have to have latitude dynamics, longitude dynamics, v dot, gamma dot, then there is a psi dot equation also, and things like that. All these things you have to talk together, all these 6 equations actually. Okay. And remember this omega e, big omega e is Earth rotational rate actually. Whatever 2 pi rotation over 24 hours, whatever that value comes in radian per second, that you have to take here actually. Okay. And so, this if you see this is more and more relevant to this, okay, this reality and all that, but depending on the application we will talk about that. For we will have to select a particular dynamics. For example, if you are just firing a small gun or a small artillery, you really do not need to talk about all these complicated thing here, okay, because the range is small, the time of flight is small, things like that. But if you talk about a ballistic missile application or a satellite launch vehicle, things like that, then you have to be very careful about accounting for all that. Okay. So, depending on the application we will have to select whatever appropriate thing is suitable for us actually. So, these are the various notations which go along with all these equations actually, that is also I will listed it out. Okay. This especially there is a bank angle also, there is a lift vector turning, the vehicle can bank, and that will result in that. And this if you have this velocity vector can now be resolved into both gamma and psi. Okay. And this is if you consider a plane horizontal parallel to this local horizontal, and there is a velocity vector direction, this is a projection of on that plane. So, that whatever gamma this velocity vector makes, this is flight path angle, and with respect to a reference line, this is actually heading angle psi. Okay. So, this is how we have to visualize the problem, and theta is longitude and phi is latitude, all sort of things are available here actually. Okay. So, all these variables, interactions, everything is given here. Anyway, so these are still point mass equations, remember that. Okay. And here you can think that okay, we have taken sufficiently complex problem, but things can be even more complex sometimes. That people tell okay, what about oblate Earth effect? That means this Earth is really not spherical. Okay. On North Pole and South Pole, they are really flat actually. Okay. So, if you have oblateness of effect coming into picture, then there are correction terms available actually. Okay, depending on if you really want to go towards North Pole, then things will be slightly different there, and then correction terms will be available associated with this actually. Okay. We will not go too much into that actually. For all our many applications, starting from artillery to kind of munition to aircraft to missiles to launch vehicles, everything, it will fall under this set of equations actually. Either you consider flat non-rotating earth, or you consider spherical but not rotating earth, or you consider spherical and rotating earth. This should be good enough for many practical applications actually. Okay. Only on very high accurate missions and things like that, especially ballistic missile applications, we talk about this oblateness corrections and all that. Otherwise, it is not typically not needed actually. Now, okay, these are still what we discussed is all point mass equations. Then the more detailed dynamics will come from what is called a 6 degree of freedom motion actually, 6 degree of freedom model. So, how do you describe that part of it? And this particular class, whatever time remains, I will not be able to completely derive that, but I will derive a significant portion of 6 equations actually, and we will follow on that in the next class also. And if you remember one of the previous classes, especially lecture 7, this is some of these concepts in a very rudimentary preliminary way we discussed actually. So, if you see any flying object, we talked, okay, there are very basic forces acting on that. One is weight, one is drag, and then there is a thrust force to counteract the drag, and then there is a lift which will balance the weight. Along with that, there is a side force, but typically these side forces are balanced out in a good flight actually. Even in turning, when you call coordinated turn, the side forces will be balanced out actually. So, they will, all the forces will be there, but side forces will be kind of very close to 0 basically. We do not want side forces actually anyway. Anyway, these are basic forces. And then there are basic moments about these axes. Now, we remember we talked about the body axis frame, and we visualize at the CG an axis frame now, because 3 direction motions here to talk about, and there is x axis, there is a y axis and the z axis, which will form some sort of a left handed coordinate system actually. Okay. A left handed coordinate system where your forefinger will point towards the nose cone, okay, and then your thumb will point towards the y axis, and the middle finger will point to the downward direction z actually. Okay. These axis frames are very critical in understanding the 6 equations, because you have to resolve these motions of the vehicle in all possible directions actually, all these 3 directions. Now, once you define the coordinate frame, you can grab your finger in the right hand coordinate frame sort of thing, and then this your point, if you point your thumb to the fore side, then the directions of these your other fingers will give you the positive direction of the rolling action, pitching action, things like that actually. Okay. So, if you have x, y, z defined that way, then the positive roll will be like that, positive pitch will be like that, and positive yaw will be like that. So, these are the notions we have to remember before understanding anything more actually. So, we basically talk about these forces, okay, ignore side force for a second, then you have weight, lift, drag and thrust, and then we have this roll, pitch, yaw motion actually. Okay. So, in this this axis frame is still available to you. So, remember this is x axis, this is y axis, this is z axis here, and this is what you see here x, y, z. So, along this x, y, z we have forces, and around this x, y, z we have moments actually. Okay. So, force level equations will come from will define this translational dynamics, and moment level equations will define this rotational dynamics actually. Okay. So, that is where you have to see that, and there also we discussed about this control action, then how these control actions can be accounted for, and we saw that this aileron motion, ailerons are typically employed for rolling about x axis. Okay. So, that is the job of the aileron, and then we discussed about the pitching action, which is through this elevator action. Okay. You can this is a rotational motion about the y axis, that is a rotational motion about the x axis. Okay. And then we talked about a rotational motion about the z axis also. So, all these 3 things are possible as far as rotational motions are there, and translationally it can go in x direction, it can have a component along y direction, it can have a component along z direction. So, all these translational 3 and rotational 3 we will have to discuss, and remember Newton's laws are all second order equations. That means, you have 6 second order equations which will essentially result in 12 first order equations later. Okay. So, that is what we will have to derive and see the integrated relationships and all that actually. And these are all coupled in a way, because they, depending on what you are talking about, you can visualize an approximately decoupled system, but in truly speaking they are all coupled with each other actually. So, we have to account for all these coupling effects and things like that. So, let us see what we discuss here. So, assumptions involved again. Okay. First, we will start with flat earth assumption. So, spherical and rotational effects are negligible here, and models are available, so which will account for that also. So, this is not the restriction that we have to really deal with, but to understand the equations, this is good enough actually. Then we also assume the vehicle is rigid body, that means there is no relative motion of particles and no spinning rotors also. So, we are not talking about like helicopter motion, things like that actually. Okay. That will have a slightly different mechanics coming into picture, and that is why helicopter dynamics is also a lot more complex than aircraft dynamics really. Okay. We are considering here aircraft dynamics and probably launch vehicle and missile dynamics here. And then we also assume that there is a constant mass as well as mass distribution. That means, we do not talk about theoretically speaking, we do not talk about fuel burning. Okay, that means, we do not talk about CG movements and all that. Okay, CG remains fixed, the mass remains fixed, the no fuel loss happens, no passenger movement in the inside the aircraft. Lot of assumptions holds good. But remember, passenger weight is hardly a fraction of the entire weight. So, that is justifiable motion actually, justifiable assumption really. We also talk about uniform mass density. That means, if you see anywhere, the density of the aircraft remains same actually. Okay. So, ultimately it is not a very strong assumption either, because we are all talking about rigid body motion where this effect of density is integrated over the entire volume. We will see that is where this moment of inertia, other things will come actually. Okay. So, this is not a very strong assumption either actually. Then again we assume constant gravity force remains constant throughout the airplane body actually, which is very much justifiable. Aircraft is just such a small object compared to earth dimension basically. It is just that is a theoretically justifiable reason actually. So, we just put it, we do not talk about, see, theoretically speaking, gravity can vary along with height, but we do not talk about that much height variation here. So, that we have to account for that gravity variation with respect to height. So, we will not talk about that actually. So, under all these assumptions, let us see how you derive all these this complicated kind of equations of motion. And here we are also we also have to visualize one more axis frame, which is called as inertial axis actually. Okay. It is a non-rotating and non-moving axis frame. Okay. Typically, it is let us say launcher point for the launch vehicles, or let us say like a airport for aircraft application, or it can still be an imaginary point somewhere on the earth. Okay. So, and sometimes people tell, okay, it is fixed at the center of earth and things like that. So, we will not discuss too much on that. All that you are telling is there is a inertial axis, okay, and then there is a body axis which moves along with the body. Inertial axis does not move, but body axis moves actually. Okay. And if the aircraft is oriented, then the body axis is also oriented along with that. Okay. Because body axis is tightly fixed with the body basically. So, if the aircraft turns, the body axis also turns basically along with that. Okay. Now, if this axis, this body axis moves along with the aircraft, then on that axis frame we cannot define the position of the aircraft. Okay. Because in that axis frame, the position of the aircraft is always 0, 0, 0. So, we cannot get a information of position of the airplane actually. So, what we have to do, and as well as attitude of the airplane, because if the airplane is rotated, the axis frame is also rotated. So, the attitude information is also lost actually. In the body axis, the attitude angle is always 0 and the position of the vehicle is always 0. So, for that reason we need another axis frame which is decoupled from those behavior, and hence we can visualize the position of the vehicle as well as attitude actually. That is where this inertial axis comes into picture. Okay. Now, let us say from simple geometry, now we will consider some geometrical aspects and all that. Okay. And if you see this, we will consider this vector as Rp, okay, and we will consider this as some particle on the aircraft, somewhere in the aircraft. So, that vector is R, R prime rather, or this is Rp prime and this is R actually. Okay. So, then if you consider this from simple geometry, this R prime rather is nothing but Rp prime plus R actually. Okay. and because P is the center of gravity or center of mass in a uniform gravitational field, center of mass and center of gravity are same anyway. So, we talk about P is the center of mass, and hence if you consider this is nothing but dm, rho a is density of the aircraft, okay, dv is the control volume that you are talking about. So, if you just take r times this dm and integrate over the entire volume, obviously that is 0, that is the definition of center of mass. Okay. Around center of mass, if you just take every individual particle and then do this volume integral, then it should come to 0 actually. So, if you substitute this r, this is r is nothing but this relationship r prime minus r p prime. Okay. This r is nothing but this minus that. So, you substitute that, and hence what you get is this integral of this r prime rho dv, okay, this particular thing is equal to that is there. Okay. But you also know that r prime, okay, what is there actually? This particular r depends on where you are situated actually. Okay. But this particular rp does not depend on this particle particle location. The rp is at the CG, that is all. So, I can take out this rp outside the integral, okay, and consider, okay, this because of this is nothing but the entire vehicle mass actually. Okay. So, hence my rp prime, that is essentially the vector which will give me the position of the aircraft, okay, with respect to this inertial frame, that is nothing but this actually. Okay. So, this relationship we will use it later actually, just keep that in mind. Now, we will derive this dynamic equations, and this kinematic equation will derive next class actually. Dynamic equations are little more complex, kinematic equations are not that complex to visualize actually. Okay. So, dynamic equations are the equations which will directly see Newton's second law of motion actually. Okay. Now, if you consider this airplane again and then want to apply this Newton's second law and things like that, there are two ways we have to you can we have to apply that. One is the linear momentum and another is the angular momentum actually. Okay. So, rate of change of linear momentum, this is the linear momentum of the particles integrated over entire volume. Okay. So, the total linear momentum, and this is rate of change of total linear momentum, is nothing but total applied force. Total applied force is one is the gravity force, okay, another is aerodynamic force. Remember, aerodynamic force depends on surface area basically. Okay. If you integrate it over the entire surface area, then you will get something. So, this is surface area integral and this is a volume integral, okay, m times h and all that actually. Okay. So, rate of change of linear momentum is total applied force partly through gravity and partly through aerodynamic and thrust forces actually. Okay. And similarly, rate of change of angular momentum, okay, is almost same expression, but there is a cross product that you have to take with respect to r prime actually. Okay. Remember, that is your r prime. Okay. So, you have to talk about that, and that the rate of change of that is the angular momentum is nothing but again r prime cross that whatever force you have, and then r prime cross that whatever force you have. So, this is nothing but rate of change of angular momentum is equal to the moment generated due to gravity force and moment generated due to thrust and aerodynamic forces actually. Okay. Now, let us analyze this equation slightly more and then tell, okay, what is going on here actually. Okay. So, this is what we want to analyze here, and remember r prime, okay, r prime is nothing but rp plus r actually, right. So, this is what you will substitute here, the rate of change of this force that you are discussing here actually. Okay. Then this is like this, okay, and remember this integral, this derivative I can take outside the integral now, okay, because finite volume integral anyway, and then I try to kind of visualize simplify this actually. Okay. So, this dy dt out now, and then I talk actually, okay, rho a times dv. Now, rp, okay, this has nothing to do with this mass distribution where it is located actually, because rp is directly this vector. So, I can take out outside the integral, okay, and then I leave with this r is this this volume integral. Once I want to take this volume integral, this r I cannot take out of that, okay, because this r is inside this volume, it is a function of this where it is located actually. So, I cannot take out that, but RP prime I can take out, because that's independent of where this fellow is situated actually. Okay, so with that, and then again what is this actually, because that is by definition, okay, this is nothing but 0, because that is say, just one second. Alright, so this is that nothing but center of mass. So again that is by definition of center of mass, this is 0. So we are left out with this d by dt, again d by dt of this fellow is mass, total mass of the vehicle, and something like this actually. Okay. So we are left, ultimately you are left out with m into dvp by dt. Okay. So this velocity vector whatever is there with respect to this center of gravity, the total velocity vector will pop up is like that, m into the total rate of change of this entire velocity vector. Okay, that is all we are talking here, this entire expression actually. Okay. Now, okay, what happens here? Okay, this particular thing, this is all about left hand side. What about right hand side? Okay, right hand side terms are nothing but this is easy, because gravity is constant, uniform gravitational field, that is what we talked about, and this integral is nothing but the entire mass of the vehicle. So it is having m times g basically. And this thrust is okay, this is actually a surface integral, it is not a volume integral. Let me correct that. Oh. Okay. This is surface integral, this is nothing but aerodynamic force and thrust force actually taken together. Okay. So what you have here, this is like this is the left hand side that we saw. Okay, left hand side expression is equal to the right hand side expression. Now, this gravitational force is nothing but mg. So that is, remember these are all in vectorial notation actually. So with all the components level and all we have not discussed yet. This is the total vectorial thing that we are talking here actually. So mg plus this aerodynamic force is the x vector, and thrust force is nothing but xt vector. Okay. So this is how the relationship turns out in the vectorial notation actually. Now the problem here is thrust forces are typically applied in the body frame, they are not applied in the inner shell frame. Right, what you discussed here, all these things, Newton's laws are, remember, they are valid in the inner shell frame. Okay, they are not valid in the body frame, because body frame is really not an inner shell frame. Right. So what happens? The thrust force is typically, but the thrust and aerodynamic forces typically happen in body frame anyway. All forces moments happen, they are acting on the vehicle in the body frame. So aerodynamic forces typically act on what is called as wind frame, which is actually close to body frame, and they are exactly same when alpha and beta are 0, angle of attack and side slip angle, when they are 0, then these things happen to be 0. More on that you can see from applied dynamics book actually. Okay, so body frame is a rotating frame, and hence it is not an inner shell frame. So the locking effect that is coming here is, we cannot rely on this thing as it is actually. So we have to take the help of something else before we visualize the components of the forces actually. Okay, so they are, because Newton's laws are not applicable directly in the body frame. Okay, what we saw here is all happening in the inner shell frame actually, everything happens in the inner shell frame. I want to have a body frame, the body frame levels of equations of motion, because that is where the real action takes place as far as forces and moments are concerned actually. Okay. So if I really want to visualize in body frame, then I have to talk about a standard results in vector theory. Okay. If you take any vector A, okay, then this equivalent to what will interpret in inner shell frame is nothing but S n in the rotating frame, that you take about whatever rotating frame effect, plus this omega cross A, the rotational rate will come into picture. That's okay. So whatever angular velocity of the rotating frame with respect to the inner shell frame, that is omega, and A can be any vector. So this relationship we have to account for if you really want to apply that in the body force actually, in the body frame. So the same equation that we have here, suppose I want to apply that in body frame, then the left side of the equation I have to modify that and tell, okay, now that is valid. If the right hand side happens to be in the body frame, then the left hand side should be this way, not the other way. Okay. Otherwise, if the right hand side happens to be in the inner shell frame, I can simply live with that. Okay. So this is where the critical relationship comes actually, and this is where it will generate this what is called as Coriolis components actually. Okay, these are this omega cross Vp, which is actually that actually makes the aerospace dynamics complicated, if you ask me. That is the only reason why the aerospace equations look complicated actually, because this cross product thing you have to account for that all the time actually. Okay. Anyway, but we have a relationship now, so we do not have to be confined with respect to unnecessary linear cell frame. So, let us visualize this expression all happens as it happens in the body frame actually. So, before we before we move along, we will to decompose this. Now, we will decompose this vectors notations into components now. So, this entire rotation rate consists of P, Q, R. P is about x axis, Q is about y axis, R is about z axis, like that in the body frame. Similarly, Vp, the total velocity vector will have u v w component, the total position will have x y z component, like that actually. So, you decompose that. This x, remember, are aerodynamic forces. Okay, this is not position coordinate, they are forces actually. Similarly, thrust forces will be decomposed into x t, y t, z t actually. Gravity also will have a component x, g x, g y, g z, because this x y z is not parallel to the inertial frame. They are oriented with respect to inertial frame actually. Okay. Now, this omega cross Vp, this particular term we have to evaluate that way. This matrix form, determinant form, like that actually. Okay. We know that the cross product evaluation basically. Okay, you have to evaluate this sort of a determinant notation basically. Okay. And this is okay. If you really want that, then probably you have to put one more bar here. Okay. Determinant there, and then it is like if you evaluate that. So, I times this q times w minus v times r minus z times p times w minus u times r plus k times this p v minus u q. So, all that is there here actually. So, this term, okay, I can write that in I j k component in the body frame like that actually. Okay. So, once I do that, this particular thing, other things are very straightforward anyway. Okay, this is in body frame. So, this is m u dot, m v dot, m w dot. Okay, this is very straightforward. M g x, m g y, m g z will be there, and this will have x y z component anyway basically. So, now taking into account all that, I will be able to write this equation that way. Remember, this is the first mu dot comes from here, then this I component of that, which is nothing but this component actually. Okay. So, that will come here. Okay. And then that is equal to the gravity component and all that, m g x will come here, and then this is this x direction sources actually. So, that will remain there like that. So, similarly, it will happen to all u v w components actually. Now, what about g x, g y, g z? Eventually, it can be derived in a more formal way, this components and all that. Now, this attitude angles will come into picture. It is a function of this pitch angle theta and roll angle phi basically, and very quickly you can visualize that this is the gravity force that is acting along. So, if the aircraft is pitched by angle theta, then this particular component g x, remember g x is opposing to this x direction basically. Okay. So, this particular component will be nothing but minus g sin theta basically, this angle is theta. So, we will have a sin theta component along that direction basically, little component there. Okay. So, that is where it will have, and then if it is not only pitched, but after pitching it is also rolled actually. Okay, this is a pitch angle, there is a roll angle also, and then this roll angle will generate these two components actually. So, one is g sin theta, which is opposing to x vector, then g cos theta will have two more components, g cos theta into sin phi and g cos theta into cos phi. So, one will act along the y direction, one will act along the z direction. It can be derived more formally also, we will try to see whether next class probably, but pictorially you can see that. Okay, one component what is coming as mg cos theta here, that will have two more components depending on this phi angle actually. Okay. So, mg cos theta resolved into this cos phi sin phi component will act along that actually. So, once you put that together and then try to sort out what is u dot v dot w dot, that is where you will get u v w dot actually. Okay, we will see, you got it right. You put this here and then solve for u dot equal to something, v dot equal to something, w dot equal to that. So, you will get 3 state equations from there. Okay. Now, these are all about force level equation. What about moment level equations? Okay. Again, moment level equation we have seen, this is the left hand side of the equations. Okay. And then this can be derived from inertial frame to body frame through certain algebra and all that. You can see that details in this particular book. But I will try to simplify the matter by directly applying these forces, these moments in the body axis itself. Okay. So, and remember that the resulting moment of the gravitational field about the center of mass is 0, because it is a uniform gravitational field anyway. Okay. And right, I mean the gravity force is acting everywhere in the same quantity actually, all the particles of the vehicle. So, it will not result in any specific moment because of gravity. The entire vehicle is pulled down basically. There is no rotation effect, there is no differential force in between the different molecules and all that actually. So, I will ignore that term and then proceed further actually. So, what you have, this is nothing but modified angular momentum term for rotating from effect. We have noted that already, that this also has to be taken into account. That is where it makes the complicated actually, makes life complicated, because that vector A can be any vector, and this applied momentum is also a vector. So, you have to talk about a rotating effect which there also actually. So, what is that? Okay. So, this particular term what you see in the left hand side, okay, this d by dt of that, this is nothing but that, okay, and this particular thing, okay, this is the d by dt of A cross B, okay. So, that is d by dA by dt cross B plus A cross d by dt of B basically, okay. So, you interpret that as A vector, that is a B vector. So, d by dt of A cross B is nothing but dA by dt cross B vector is that, plus A vector which is R cross d by dt of B vector. Okay. So, and if you simplify this is any vector with a cross product with respect to that particular vector is 0, we know that cross product of the same vector, that is 0, and then that is what is left out is again d by dt of that, again that has to be resolved into this vector notation components actually. So, this particular thing is nothing but first is r dot, okay, then plus omega cross r also, okay. This particular quantity what you see here, we cannot directly apply that actually, okay. You have to apply through this angular relationship actually, this cross product relationship. So, that will result in r dot, and remember r dot is 0 because we are there is no movement of the particle with respect to the body frame axis, okay. So, a particles do not move, they do not vibrate, I mean there is a rigid body airplane, right. So, because of rigid body dynamics r dot is 0, okay, and then we are left out with only these quantities. By the way, this book derives this equation in a slightly more complicated way. I have tried to simplify it as much as possible actually, okay. It keeps this here and then derives, then further down the line it takes it 0 actually, it will result in double dots and things like that. We do not need to do that, right away put it 0, okay. That is what it is actually. Then we talk about, okay, this particular quantity, okay, what you have here, okay, this results in this particular thing, okay, r cross d by dt of omega cross r, right, that is what you are left out with. Again you have to apply this moment or this rotational effects and all that. So, r cross, okay, d by dt of omega cross r. So, this is r cross del by dt of omega cross r plus omega cross r, again and again you have to keep on applying that to simplify that actually, wherever you see d by dt you have to keep on applying that way actually, that is where things become more and more complicated basically. But nonetheless it is I mean you can make it, you can track it basically what is happening. So, if you simplify these equations, now you put it there and then omega dot and then r and then r dot is 0 again, and you will be leaving out with that actually, okay. So, the moment equation if you see this left hand side is something like this complicated expression what you see here is nothing but the applied moment actually through aerodynamic as well as thrust. So, this is rate of change of angular momentum is through that, and then you have to simplify that obviously in a component level thing. There we have to talk about some standard results in vector theory again. So, you have a triplet basically A cross B cross C, okay, that relationship you bring in, and then you try to put in all this expression again A cross B cross C, and then C also is two products and all that actually. So, you apply all these, it is not difficult to kind of see this long end algebra, and then R is nothing but XYZ components in the body frame. In the body frame, remember that is not the position of the vehicle, it is XYZ with respect to the center of gravity of that particular DM that you are talking about, that particle actually, okay. So, XYZ is the distance from center of gravity of that control mass or something, control volume what you are talking, okay. Now, omega has PQR components, and then you are able to kind of decompose that, because you know this, what is beauty of that, entire thing now results, I mean whatever this cross product will have dot products now. Dot products are nothing but scalar components, and then we will have 1 vectors associated with that. So, that is easy to simplify after that actually. Okay. So, you put that all these things together and then try to solve, try to simplify. This results in dm. So, it will go through this for example, this one r square is nothing but x square plus y square plus z square. Okay. And similarly, r dot omega dot actually that will result in that, because these are all dot products now, it's easy to see that. And then once you simplify this thing, it will result in some expressions like that. And this is need to see, because all these things are nothing but moment of inertias. These terms what you see here is nothing but ixx, this term what you see here is iyy, this is izz, principal moment of inertias, and these terms were nothing but cross moment of inertias actually. So, as long as the rigid vehicle dynamics is concerned, I really do not need to know the mass distribution and things like that, I just need to know the lumped quantity called moment of inertia. Okay. So, that is typically supplied to us actually is for the control designers actually, supplied to us from structural engineers essentially. So, this entire quantity in terms of moment of inertia, I can write it in a very neat way. So, entire thing which looked so complex here, okay, this level is all reduces to, in terms of moment of inertia, this rather simple looking expression basically. Okay. Similarly, this other component that we left out can also be derived, okay, in a similar manner, and you have equivalent expressions like that actually. So, you have this term, you have that. Now, put them together and then bring in the assumption that airplane is symmetric about xz plane. In the xz plane, if you tear the aircraft, it is all symmetric with left and right side. So, in that situation, ixy and iyz will be 0, this cross moment of inertias. And in addition to that, missiles and launch vehicles will have symmetricity about xz and xy plane both actually, they are symmetric about both the planes. So, all these cross moment of inertias will be 0 in those situations. Okay. Otherwise, this is anyway true for aircrafts also basically. So, that will bring in further simplicity in these equations basically. Okay. So, you will be left out with only these equations later actually, okay, what you see here, okay, because applied aerodynamics components are LMN and thrust are like that. So, that is you are left out with that. So, you can solve this P dot Q dot R dot from here, because remember this is a linear equation anyway, it is very clear here. This P dot R dot are coupled through Ixz. The moment it is not there for missiles and all, this is also even not there. So, directly you get P dot Q dot and R dot here. Because Ixz is not really 0 for airplanes, you will have some coupling effects for P or R actually, P dot and R dot, but nevertheless these 3 equations are linear. So, you can solve it and then get it for P dot Q dot R dot. So, what you are getting here ultimately is this force level equations and this moment level equation actually. And if you solve this for u dot v dot w dot here, p dot q dot r dot here, that is where you get it actually, u dot v dot w dot and p dot q dot r dot. So, these are what is the force level equation, this moment level equation, these are Coriolis component, comes from rotational effects and all that. This is gravity term, okay, and this is the aerodynamic and thrust moments, external forces. And similarly, here the gravity term does not come, remember that, okay, moment level gravity does not play a role. And this is the coupling equation that you talk about. Here the control surface actions will be significant here, by the way. This will be have a very minimal effect, aerodynamic control surface action basically. So, details will be I mean once you understand these details, you will be seeing these things actually. So, this now this C1, C2 what you see, again this C1, C2, C3 all these are functions of moment of inertia, which is given like that. It can be easily solved. I mean from these equations what you have, you will solve for P dot Q dot R dot. As a byproduct, you will be able to solve this actually, and you will get C1 to C9, all the things are like that actually. So, it is easy to compute these constants actually. And then force and moment equations makes life more complicated, because of these aerodynamic forces and thrust forces and all will be given and the several component level equations considering various angles and things like that. So, this particular thing, this remember x t y t z t is force level equation, I mean, and then L T M T N T are the like moments and all that. So, all these expressions you have to put it together in those equations to get this force and moment level equations actually. Okay. That is where this dynamics becomes complicated. However, once you understand this, I mean this is we still can talk about all different directions of the velocity, I mean you can in a component level and as well as moments actually. Okay. So, this is all dynamic equations. So, kinematic equations and all I will talk in the next class actually. Thanks a lot.